So, in the previous lecture we derived the expression of kinetic energy in terms of the speed of the particle. So, if we have a particle of mass m naught, we derived that kinetic energy is m naught c square divided by square root 1 minus v square by c square. This v here is the speed of the particle. Particle is moving with speed v, and then minus m naught square. This is the expression we obtained from the very basic definition that if there is a force on the particle and then the force does some work. So, the work done by the force on a particle is equal to change in its kinetic energy. So, starting from there we derived this expression, which is very different from half mv square. Now, what happens if the speed of the particle is small as compared to c? If v is 0, the particle is not moving, kinetic energy should be 0. So, if you put v equal to 0, then this is 1 and m naught c square minus m naught c square is 0. So, at v equal to 0, this equation is fine. But for small velocities, non-zero speeds, I should get our familiar expression half m naught v square. So, let us see what happens if v is very small as compared to c. If v is very small as compared to c, then you can write this expression as this kinetic energy as m naught c square, and this is 1 minus v square by c square to the power minus half, and then minus, or I can take this common, minus 1. And since v is very small as compared to c, this quantity is small as compared to 1, and I can use binomial theorem and retain the first non-zero term. Remember that minus 1 is there. So, this is m naught c square. What is binomial theorem? Binomial theorem is 1 plus x to the power n is 1 plus n into x plus something n minus 1 bifactorial 2x square and so on. This is the series and is valid for x less than 1. So, if x is much less than 1, then higher terms involving x square, x cube, those will be negligible. So, here we will be using this equation and 1 minus v square by c square to the power minus half. So, it is 1 plus x to the power n. So, first term is 1, good. Next term is plus nx, this exponent and into this x. So, this minus half into minus v square by c square. So, it will be plus half into v square by c square, and then the higher terms x square, x cube. So, v square by c square, square and cube and all those things, and minus 1 is here. So, this minus 1 cancels with this minus 1, but this remains, and therefore, we need not write any other term. Next term will be v4 by c4, square of this is already small and square of this. So, the first non-zero term we will retain, that is the way we do approximations. Now, you can see what it is, this c square will cancel with this c square and you have half m naught v square. So, yes, if speed is small, speed of the particle is small as compared to the speed of light in vacuum, I can still use kinetic energy as half times mass times speed square. But if it is large, if it is comparable to c, then of course, I cannot do this analysis, because then v by c is not very small as compared to 1 and I must retain higher terms also. Then you have to use this exact expression, this is the exact expression. So, that is about the low velocity limit. Now, let us talk about this rest mass energy once again. This we call rest mass energy. and kinetic energy is the energy coming because of the speed, and this we call total energy. This we call total energy, E. So, of total energy E, you have a part which is rest mass energy and a part which is kinetic energy. So, if I have a particle which is not moving, we still say that it has energy, and that energy is its rest mass energy. Because of the mass there is an energy, and that energy is m naught rest mass into c square, and you give kinetic energy that is added on top of this rest mass energy. So, for a single part it is fine. What about a particle which has sub parts? For example, this chalk here, it has large number of molecules. So, if I use this chalk as my particle or my object and it is at rest, so what is the rest mass energy? I can think that okay, for each subpart, for each molecule, whatever calcium carbonate or whatever, for each molecule we can calculate the rest mass and then we can add that. What will be the rest mass of calcium carbonate? You have calcium, you have carbon, then you have oxygen in a particular fashion, bonded in a particular fashion. You may think that it will be the rest mass of carbon, calcium, and then all that 3 oxygens I can add to get that. But that really does not work out. That does not work out. For example, take hydrogen atom. It has 2 particles in it, proton and electron. So, let us talk of hydrogen atom. You know, hydrogen atom is made of a proton and an electron, and they are bonded. So, P and E, and they are bonded. The simple picture that we draw in schools is that you have a proton here and then electron is going on a circle. This is a simple picture which we draw. Whether it goes on a circle or not, hydrogen atom is a combination of proton and electron bonded together. And we say that in ground state, in the lowest energy state, the energy of hydrogen atom is minus 13.6 electron volt. So, you must have done all these things in schools, that the ground state or lowest energy state, the energy is, that is how we write, minus 13.6 eV. What is this energy E? This is not same as this energy E that we write here, total energy. No, this is if this proton and this electron, if they are not bonded and we supply some energy and we separate, we ionize this hydrogen atom, we remove this electron from this atom. So, now the electron is separate and the proton is separate. Separate means the separation is now large. So, if you have a proton and an electron which is not bonded, no bonding, this is a combination of proton and electron, but when they are bound it becomes hydrogen atom. Now, compared to this energy, if you call this energy as 0, then this energy is minus 13.6 eV. So, when we draw our diagrams, this is energy equal to 0 and then we say that energy is minus 13.6 eV. This is when the proton and electron are separated, and this is when they are bonded. This is when they are bonded, and bonded also can be in different fashions. So, you can have ground state, you can have first excited state, second excited state. In first excited state, the energy is minus 3.4 eV. then you have second excited state and third excited state and so on, and finally you have E equal to 0. The rest mass energy of this combination is not 0. We say that if I call this as E equal to 0, then this is minus 13.6 eV. But when we consider these equations, the relativistic phenomena, we will say that proton had some rest mass, right? The proton had some rest mass which is about 938 MeV by C square. Mass, I am writing mass of the proton, rest mass of the proton, and mass I am writing in unit MeV by C square. This is a very common unit of mass used by atomic physicists, nuclear physicists, then people working with quantum mechanics. They use these kind of units for mass. You know, E is energy is mc square. So, m is E by c square, and energy, one unit of energy is electron volt. SI unit is joule, but then you also talk of electron volt. So, you know how many electron volts will make 1 joule, or how many joules will make 1 electron volt, that conversion you know. So, by C square. So, if I measure this energy in electron volts, this unit will be electron volt by C square, and MeV is mega electron volts by C square. So, this is unit of mass. So, mass of the proton is this, and mass of the electron is 0.511 MeV by C square, or 511 keV, kilo electron volt by C square, that is electron. So, if you have a proton and an electron which are separated from each other, no bonding, it is not hydrogen atom, then the rest mass of this combination will be this plus this. But if it is 0, then this energy is minus 13.6 electron volt, right. So, if this energy is 938 MeV by C square plus 0.511 MeV by C square, it is 930, it is not, we will say no, the energy here is 938.511 MeV C square. The sum of rest mass energies of proton and electron, then this energy will be 13.8 eV less than this energy. So, mass will accordingly, okay, this is mass, this I am writing mass. M naught, rest mass, this proton is at rest, this electron is at rest, this is all rest mass, this is all rest mass. So, rest mass is this much. Here, when it is hydrogen atom in ground state, the rest mass here is of hydrogen is 938.511 MeV by C square minus 13.6 eV by C square. So, the mass of hydrogen atom, rest mass of hydrogen atom is less than sum of rest masses of a proton and an electron, although hydrogen is made from proton and electron. So, in that bonded state this happens. So, rest mass of a composite particle which has subparts will depend on the internal structure. So, here the internal structure is different, here the internal structure is different, here the internal structure is different. First excited state, you give some energy and the hydrogen atom reaches here in this energy level, first excited state, it is still at rest. atom as such is still at rest, atom is not moving. So, it is rest mass only, but then this rest mass which is in the first excited state will be 938.511 MeV by c square and then minus 3.4 EV by c square. From here it is 3.4 EV less. So, rest mass is different here, different here, different here. So, if you have a composite particle which is made of subparts and these subparts internally they can move, internally they can interact with each other, then the rest mass of that composite particle will not be equal to sum of rest masses of the constituent particles. I take another example. Let us say helium, alpha particle. So, alpha particle, what is alpha particle? Alpha particle is nucleus of helium atom. So, nucleus of helium atom is 2 protons and 2 neutrons bound together in a very small volume, that is helium nucleus, which is also called alpha particle. Now, if you consider the 4 particles separately, P here, N here, N here, not in a nucleus, but separated from each other. What is the rest mass here? The rest mass here will be, m of this will be rest mass of proton into 2 and plus rest mass of neutron into 2, or rest mass energy if you write in this combination. This is rest mass, and rest mass energy if you write rest mass energy. No kinetic energy, it is not moving, this is not moving, this is not moving, this is not moving. So, for this combination the rest mass energy is c square, this multiplied by c square. So, it is 2 mp plus mn times c square. So, just addition of 2 proton rest mass energies and 2 neutron rest mass energies. But then when it becomes a alpha particle, when these 4 particles are bonded together so that they make a nucleus, helium nucleus, which you call alpha particle, now the rest mass energy is less. Rest mass energy of helium nucleus or alpha particle, this is this quantity 2 mp plus mn c square, this quantity minus about 28 mega electron volts, 28 point something mega electron volts. So, this rest mass energy is less than the sum of rest mass energies of proton, proton, neutron, neutron. Correspondingly rest mass will be just this divided by c square. So, rest mass of helium nucleus, if you write, that rest mass will be 2 mp plus mn and then minus 28 MeV by c square. And these are experimentally measured quantities. Now, I am saying you can very accurately measure mass of proton, mass of neutron, mass of alpha particle. You have instruments and you have methods. So, very accurate measurements are available for all the nuclei in fact, and from those measurements we know that rest mass of helium is about 28 MeV by c square less than 2 times proton rest mass energy plus 2 times neutron rest mass energy. When 4 protons in the sun, core of the sun, combine to form a helium nucleus, we get energy. We get energy. From where that energy is coming? it is coming from this difference only. If you have 4 protons, and separated from each other, and then 2 of them are converted into neutrons, and then they all combine to make a helium nucleus, this kind of nucleus ppnn. So, from protons to helium nucleus, of course from proton you have to make neutrons also, and proton or neutron are slightly different rest masses, but still the rest mass 4 times mp, this is a rest mass here and this is rest mass here, and proton becomes neutron. Remember, if proton becomes neutron, the rest mass increases, because rest mass of neutron is slightly more than rest mass of proton. Neutron is slightly heavier than proton. So, if I just do not look at all these things, I would believe that this rest mass is more than this rest mass, because here you have all 4 protons and here you have 2 protons and 2 neutrons, and neutrons are heavier than proton. So, you may think that okay, this rest mass is more than this rest mass, but no, because of this bonding, this rest mass is less than this rest mass. So, it is like this, and that difference, when the rest mass has decreased, the rest mass energy has decreased, going from here to here, rest mass energy has decreased. So, that decreased energy is radiated in the form of light and all those things, and that energy we get on our earth. So, this is kind of mass energy conversion. Here the mass is decreasing and we are getting energy out of it. So, the mass is being converted into energy, but the particles remain like that. The particle is proton, neutron, so we know everything. Come back to this hydrogen atom. If you put the hydrogen atom in first excited state, you say that it de-excites, and then a photon of this minus this 10.2 eV photon is, we will talk of photons, photon is emitted. This much energy is emitted as light. So, what is happening? If you see from here to here, the rest mass is decreasing. From here to here, the rest mass is decreasing. Here it was this number minus 3.4, here it is that same number minus 13.6. So, this is lower rest mass and this is a higher rest mass. So, rest mass has decreased, and that rest mass which has decreased multiplied by c square, that much energy is made available. So, the mass is converting into energy, and that energy that you obtain, this energy here, is delta m, the decrease in rest mass times c square. Similarly, if you increase the energy of those subparticles somehow without changing the overall kinetic energy of that composite particle, the rest mass has increased. So, suppose you have a spring, in its natural length, and then you compress the spring from the 2 sides. You apply a force from this side, you apply a force from this side. So, this end moves in this direction, you have a positive work done by the applied force. From here also you have positive work. So, if you apply a force here, if you apply a force here, and then you compress it, you apply a force here and you have applied a force here, and finally, if you apply a particular amount of force, you will compress it by a particular value. So, let us say this is at rest, initially it is at rest. So, originally it is at rest, this is the original position, let us say this is the original position, natural length, it is at rest, and now you have applied forces and then it is compressed and again it is at rest, this spring is not moving, right. So, this value of compression and this force, they are related, F is equal to K spring constant times delta x, and then it is all in equilibrium, nothing is moving. So, the kinetic energy is 0, kinetic energy is 0, it is only rest mass energy. But if you have applied a force and then there is a displacement of that point of application, a positive work is done here, a positive work is done here. So, on the spring I have done positive work and therefore, its energy has increased. So, this energy is more than this energy, there is no kinetic energy, and therefore, this rest mass is more than this. A spring in a compressed state is having more rest mass than the same spring in its natural length. And similarly, if you extend the spring from its natural length, once again you are doing positive work, you are applying forces outward and the ends are also moving outward. So, you are doing positive work, you are increasing the energy, but there is no kinetic energy, finally that spring is at rest. So, increased energy, where has it gone? It has gone into the rest mass energy, the rest mass has increased. So, a compressed spring or an extended spring has more rest mass than the same spring in its natural length. Similarly, if you have an object, there is some temperature, you have molecules inside, if you just heat it and increase its temperature, this object is still does not have a kinetic energy, overall kinetic energy, this object is at rest. But we have given energy to it, we have given heat energy to it. Because of that, those subparticles, those molecules inside this object, they have started moving with more speed and etc. So, the rest mass energy has increased, the kinetic energy has not changed and you have given the energy. So, where has that energy gone? It is converted into mass and it is heavier in that sense, it has more mass. So, a hot object is heavier than colder object, the same object. When it is hot, it has more mass, when it is cold, it has less mass. So, that is the kind of a mass energy conversion that goes on in nature every instant, you can say. We most of the time when we cook something in kitchen, what we are doing? We are supplying heat to our objects, we are increasing the mass, the energy is being converted into mass. Similarly, in many cases we are obtaining energy. So, when we are obtaining energy from an object, we are decreasing energy and then the mass is converted into energy. We have a different kind of energy mass conversion that I will take in the next lecture.